To understand why certain vector calculus identities always result in zero, we can look past the equations and explore perfect mathematical balance and physical consistency. The bedrock of these identities is a perfect balance between two mathematical behaviors, symmetry and antisymmetry. Imagine two different ways of organizing information. The first is flexible and commutes, meaning the order of operations doesn't change the outcome, much like how adding 2 plus 3 gives the same result as 3 plus 2. The second behavior is antisymmetric, where swapping the order of parts flips the entire result into its polar opposite. When these two opposing patterns are combined, they behave like two perfectly matched weights on a scale. Because one pattern stays the same while the other flips into its negative, they cancel each other out completely, leaving us with a mathematical zero. This mathematical balance ensures that the physical world remains consistent. We can see this through two types of fields or flows. Irrotational fields. The mountain analogy: imagine a field that always points straight uphill, like the steepest path up a mountain. The first identity tells us this field cannot swirl. If it did, you could follow a circular path that constantly moves uphill and yet somehow returns you to the exact step where you started. In the real world, this is a physical impossibility, like a staircase in an M.C. Escher drawing. Because you must go downhill as much as you go uphill to complete a loop, the swirliness of a mountain slope must be zero. These are known as irrotational fields, common in gravity and static electricity. Solenoidal fields. The vortex analogy: now imagine a swirling fluid, like a tornado. The second identity tells us that these swirly patterns have no beginning and no end. They cannot simply leak out of a single point in space like water from a faucet. If you were to trap a swirl inside a small balloon, the amount of spinning motion entering the balloon must perfectly match what leaves it. These are called solenoidal fields, and they explain why magnetic field lines always form continuous, closed loops rather than starting or ending at a single source. These rules are not just about what happens at a single tiny point. They govern how forces and fluids behave across entire volumes of space. Through the big picture theorems, we find a bridge between the microscopic and the macroscopic. One theorem demonstrates that the total amount of swirl across an open surface is identical to the flow around its outer boundary. Another theorem reveals that the total outward flow, or expansion within a solid object, is exactly equal to the amount of fluid passing through its outer skin. Together, these principles provide a rigorous link between the local properties of a field and its global behavior, ensuring that fundamental laws like the conservation of energy and the continuity of magnetic loops remain unbroken throughout the universe.